Alright, welcome to the lunchtime video. Test is coming up faster than I can even imagine. In fact, we're approaching the 2-week mark. We're at the 3-week now, so we definitely changed from measuring the length of time until the test in months to weeks. And not only that, we're starting to get down to less than 2 weeks. So measuring it in days is just around the corner. Alright, so let's continue to work as efficiently and as thoroughly as we can. We're still working on multicast. Unfortunately, it's been a little bit of a disaster. The labs, all the instructions are very, very, very unclear, to the point where they're not even clear about what interfaces are meant to connect to which devices. Even looking at the device diagram, the diagrams aren't properly labeled. It's just really, really unclear what the configuration is doing, why it's doing it, and not only that, it's the write-ups, the explanations for it are a mile long. So I wonder if, because of course we've got all these topics, and I'm thinking of it if I have a page. Well, let me just use my tablet, because I kind of want to talk about this a little bit here. So yeah, I'm going to kind of draw out some ideas I have here, if I may. Nope. So okay, here we go. Sketch now, and yep, and then app. Yep. Okay. All right. So I've got a sketch pad up here, so I just need to add the URL here. So it's going to be lgr_w.8.1. Oops. lgr_w .8.1. No, I'm pretty sure this exists. I mean, it's here on my, unless I'm just completely sketch. Huh. LGR. Oh, maybe it's a capital I-G-R? Oh, yeah, it is capital I-G-R. Yeah, usually there's a mix of capital and lowercase. Okay, so let's explain. So if here's the test topics. Now, for the sake of simplicity, let's just say we have 3 topics. So what I was thinking is that we would have these 3 topics, 1, 2, and 3, look kind of more like this, where they'd get about equal time. Now, one of the things I think is more likely is that we'd have topics 1, 2, and 3 look a bit more like this, where we've got topic 1 is like that, topic 2 is a little bit bigger, but topic 3 is just most of what the test is about. I think it's probably going to be more like this than this. Unfortunately, this is how I'm studying my time, because studying for the test, because I don't have this. So this would be really useful if I knew what this one was that took up most of the pie, so then I could take up most of my study on that. But unfortunately, I don't have that information. Now, the reason I'm bringing this up is because, from what I could tell from the documentation and all that sort of stuff, as far as learning about the subject matter, it very much seems like multicast is a 3 or a 2. So, in terms of, if this is the on the test, and then we've got another one for depth of topic, it appears to me that multicast has a lot of depth of topic. This whole, yeah. So, but of course, if it's on the test, but it's just one of these. Even though it's got so much depth of topic, unfortunately, I shouldn't be spending that much time on it because there's other things that will give me more points. So I don't have that information, unfortunately. I did want to get those thoughts out there and kind of real thought out and clear in my own mind. I think that's gonna just help me feel better about my study. But it is unfortunately eating into my study time. So let's move on and use my time more effectively. Okay, so we're going to be moving on. We're no longer going to be studying PIM-SM, which stands for Protocol Independent Multicast. Something sparse mode, sparse mode. I guess I'm not sure what it stands for. Let's go look it up again. Source specific mode, and that's a alternative to ASM. So we can focus only on source specific mode. Yeah, so let's just do a quick refresher of what SSM is since I couldn't remember the acronym. Traditional multicast forwarding is performed using multicast group addresses. A group address is a single IP address taken from a reserved range to forward multicast range /4 for IPv4, FF00 multicast range /8 for IPv6 to uniquely identify a group of hosts desiring to receive certain traffic. Any host within the multicast domain can be a source for a group sending traffic to the group's IP address. Each multicast packet sent by the source is replicated by the network infrastructure so that each host belonging to the multicast group receives a copy. Because any host can act a source, this multicast implementation is deemed any source multicast, ASM. Source-specific multicast, SSM, defined in RFC 4607, extends this concept to identify a set of multicast hosts not only by group address but also by source. A SSM group called a channel is identified as SG, where S is the source address and G is the group address. This is in contrast to the definition of an ASM multicast route written as *G. IANA has reserved for SSM the IPv4 address range 232/8 and the IPv6 range FF3X/32. SSM brings several important benefits over ASM because an SSM channel is defined by both a source and a group address. Group addresses can be reused by multiple sources while keeping channels unique. For instance, the SSM channel 192.168.45.7, 232.7.8.9. So this is going to be here. S is going to be this 192 address. G is going to be this multicast address. So, and then this whole thing is called a channel. Yeah, so here's the source address and here's the group address. So here we go. ASM is different, but we don't need to worry about that because we're only going to have SSM on the test. Is different than, so here we have a different source, and of course we have the same group. And hosts subscribed to one will not receive traffic from the other. This allows for greater flexibility in choosing a multicast group while also protecting against denial of service attacks. Hosts will only receive traffic from explicitly requested sources. One of the biggest advantages SSM holds over ASM is that it does not rely on the designation of a rendezvous point, RP, to establish a multicast tree. Because the source of an SSM channel is always known in advance, multicast trees are efficiently built from channel hosts toward the source based on the unicast routing topology without the need for an RP to join a source and shared multicast tree. The corollary of this, which may be undesirable in some multicast implementations, is that the multicast sources must be learned in advance via some external method, for example, manual configuration. SSM can be implemented using a subset of protocol-independent multicast, PIM, derived from PIM-sparse mode, PIM-SM, dubbed PIM-SM. Perfect. Okay, so yeah, it looks good to me. So once you have PIM-SM running, PIM-SSM is trivial to, PIM sparse mode, but this is PIM source specific mode, which rides on top of sparse mode. So I kind of studied these out of order. Maybe that's why I had so much trouble with it. But it looks like PIM-SSM is pretty easy to set up once you've got PIM-SM working. So let's work on that. And I'll do what I usually do. I'll go straight to help apropos, although it's been kind of a strikeout recently, but let's see what we got. Oh, and I will, of course, rename this. PIM-SM. Okay, so I think we're good to go. So the next step is help apropos. And I've still got a pretty good topology here. Hopefully we can go in here and kind of see where it went wrong. I did in the last one kind of make a a bad mistake. I accidentally strayed from what the documentation was telling me and just went my own way, assuming that there was an error in the documentation, which with that documentation isn't necessarily always a bad idea, but in this case it did happen to me. Okay, so we're going to do multicast. Okay, so it's going to be PIM-SM. Before we looked at PIM-SSM. Here we go. So we've got examples, multicast-sparse. And look at this. We've got a full lab to go here. We've got one for dense as well. We've got one for MBGP. We've got one for sparse dense. I'm not sure what that means, but Okay, so I'm not sure if one of these is PIM-SM. I would like to go ahead and do the lab there, however, and hopefully I'll have better luck with that than I did before. The reason I want to do this one though is because we've got configurations for all of the routers. The last lab they just gave you configuration for PE1, and then you had to kind of put the 2 and 2 together and come up with your own configurations for PE2 and the CEs. And I thought I would be able to do that. There are a number of things that are working, but unfortunately not everything seems to be working. So okay, so this is okay, so this is for the actual instance. So it looks like we've got documentation for let's see, for PE2 and PE1. Let's order these so that they make a little bit more sense here. Okay, so yep, and even more sense. Let's put 1 on the top and 2 on the bottom, and then we'll even associate this with number 1. There you go. Okay, so that looks like it makes the most sense to me. Let's take a look at the difference between PIM-PE and instance-PE. Okay, so for PIM-PE, we've got configuring PIM on the PE router, configure PIM on the router edge, PE1 router, specify a static route on the service provider, RP router, the P router. Okay, so this looks similar to what I did last. Alright. Configuring the routing instance on the PE1 router. Configure the routing instance VPN-A for the layer 3 VPN on router PE1. As part of the configuration, you need to establish the PIM instance for the VPN. Use the VPN group address statement at the edit routing instances, routing instance name, protocols PIM hierarchy level to specify the VPN group address, which is needed for multicast over a layer 3 VPN configuration. Set the RP configuration for the VRF instance at the edit routing instances, routing instance name, protocols PIM hierarchy level. The RP configuration within the VRF instance provides explicit knowledge of the RP address so that the no. This looks like ASM, because if this is star then it's ASM. So there's really no reason to study this if it's going to be ASM. This, I don't think, is a good one to work through because it's using ASM. Yeah, and it's got a rendezvous point. I don't think you need a rendezvous point for SSM. I'm confused. Yeah, but I definitely don't want to study ASM. I don't think ASM will be on the test. I think it'll be focusing primarily on SSM. But for now, we've got SM. So let's just start with the basics, actually, and read that. See, the problem is, as I was explaining in my diagrams here, and let me try to get back to it. So let's sketch now. Yeah, it was capital I, GR_W. Here it is. So yeah, as I was explaining here, there's just so much depth of this topic that if I learn about ASM, I could learn about, I would be, it's not even going to be on the test, ASM, according to what's in there. Only SSM and SM is going to be on there. So let's figure out what SM is. I think it stands for sparse mode, and then SSM stands for source-specific multicast. So we do have, I think, sparse mode enabled here, but I can't tell whether we're using source-specific or ASM. However, this is a really good clue that we are using ASM, because this is how a ASM... I forget what this thing was called. I mean, we just read about it, but it escaped my mind right away. So that's how a ASM channel is written. A SSM channel has a unique source. And then I believe an SSM okay. Yeah, so I think both ASM and SSM have rendezvous points. The only difference is that SSM, you don't have to think as carefully about where your rendezvous point is configured, because the rendezvous point is to establish a multicast tree, and you can do it without using the rendezvous point. So you might still need one, but it's not as important where it is configured on your network as it is for ASM. Okay, I'll just leave this tablet up here in case I need to draw anything later. Yep, and then let's learn about PIM-SM. So yep, this is sparse mode. So, yeah, this actually looks pretty good. So we've got protocol independent multicast, which is PIM. We already know what that means. We read about that before, but just to refresh, it's a family of multicast routing protocols for internet protocol IP networks that provide one-to-many and many-to-many distribution of data over a LAN, WAN, or the internet. It is termed protocol independent because PIM does not include its own topology discovery mechanism, but instead uses routing information supplied by other routing protocols. PIM is not dependent on a specific unicast routing protocol. It can make use of any unicast routing protocol in use on the network. PIM, protocol independent multicast, does not build its own routing tables. Protocol independent multicast uses the unicast routing table for reverse path forwarding. There are 4 variants of PIM, and we only need to learn about 2 of them. Dense mode will not be on the test, and bidirectional PIM will not be on the test. So let's only focus on those 2. The first of the 4 variants that is listed here is PIM-sparse mode, which stands for Protocol Independent Multicast-Sparse mode. And this explicitly builds unidirectional shared trees rooted at a rendezvous point, RP, per group. And optionally creates shortest path trees per source. PIM-SM generally scales fairly well for wide area usage. Okay, and then we'll skip down to the last of the 4 variants as listed in this write-up, which is Protocol Independent Multicast Source Specific Multicast, PIM-SSM. And this builds trees that are rooted in just one source, offering a more secure and scalable model for a limited number of applications, mostly broadcasting of content. In SSM, an IP datagram is transmitted by a source S to an SSM destination address G, and receivers can receive this datagram by subscribing to channel SG. And S and G are IPv4 addresses. S is going to be a unicast address, G is going to be a multicast address. Okay, so that makes sense to me. Now, I thought SSM was an alternative to ASM, but that actually doesn't seem to be the case. I don't see ASM mentioned anywhere here. What seems to be true is that SSM is an alternative to SM, and that actually, I think, makes more sense because those are in 2 separate categories. So just as you would learn about BGP and RIP-v2, because they're each ways of dynamically exchanging routing protocols, you would learn about SSM and SM because they are each variations of protocol independent multicast. They are each ways of setting up multicast. So, okay, so that makes sense. So I think PIM-sparse mode, that does involve PIM-sparse mode, I think, can involve ASM, I think, whatever that is. Well, I think ASM just basically has channels where you've got a star here and a G here, so you don't have an actual source. So I think the channels associated with PIM-sparse mode have a star and a G. So I think we're on the right track reading about that. But this really cleared it up. I'm going to make sure to add this to my notes because this was really clear. Thank you, Wikipedia article. Kind of surprised it was on Wikipedia, because once you get like really into the narrow stuff that people so here's some good I wonder if this video, oh my god, see, this is what I mean when I was here. It's like, this is a long video, and like, you know, if this topic has this much depth, but oops, let me Control Z that, there we go. Yeah, if this topic has this much depth but is only this amount on the test, you know, it's probably not a good idea to watch this full hour video. Oh man, but I probably should, because oh man, it's a focus on JNCIE candidate requirements. Oh wow, okay, so I should probably, I'm gonna watch this.
Protocol independent multicast and PIM-dense mode in detail. It is time now to move over to PIM-sparse mode. But PIM-sparse mode is very much unlike PIM-dense mode. In our last lecture, we introduced you to PIM protocol independent multicast and PIM-dense mode in detail. It is time now to move over to PIM-sparse mode. But PIM-sparse mode is very much unlike PIM-dense mode, where it's going to take more than a single lecture to cover all of the aspects of PIM-sparse mode. So we broken it down into an introduction lecture, which is this one, and then one lecture with all of the details. So today what we want to actually learn is the overall ideology of PIM-sparse mode, what it intends to do, how it intends to do it, what are the various mechanisms that come with PIM-sparse mode, what are the various entities of PIM-sparse mode, but not necessarily the back level details. That would be the content of another lecture. Now, PIM-sparse mode addresses many of the scale issues that you encounter with PIM-dense mode. So, the first major difference, that whole idea of implicit join, that you just pretend that everybody needs a copy of that stream, every single router in your network, which PIM-dense mode did, it is now discarded, it's gone away. So, the idea now is that a receiver must explicitly choose to join a multicast stream before one is delivered to them. So, in that way, if PIM-dense mode was a push model, I'm going to push all of the multicast stream to the remote corners of my network, PIM-sparse mode can refer to as a pull model. You need to have a router that has receiver pull the stream where it's at before it actually delivers that stream to the end receiver. Now they do share needs, PIM-dense mode, PIM-sparse mode. They're essentially very different protocols. They have different priorities, they definitely have different mechanisms. Now they do share some formats, which we will discuss in a different lecture, but for now, I may go back and forth comparing PIM-dense mode, PIM-sparse mode, but they are, and they're very, very different protocols.
Yeah, so it's kind of like the difference between RIP and OSPF. We're going to be focusing on sparse mode, SM, and then we'll also be looking into SSM.
Initial signal. So the end goal for PIM is to bring sources traffic to various multicast sources that is creating traffic on generation stream, and there are restless receivers. The end goal for PIM-sparse mode is the same as any other multicast router protocol. It is to get that traffic from the source, but only to the restless receivers. So the first step, as with any other multicast router protocol, is to locate the sources and locate the receivers. So it's important to go over how the sources and how the receivers actually first do their initial signal, inform the multicast network about their existence. The sources, they signal the first hop. So FHR, if you have not done that lecture or if you haven't seen it already, I highly recommend go back to it and actually see it. But FHR means the first hop router. That means these are routers that are directly connected to multicast sources. The multicast sources must inform the FHRs, which are basically the gateway into the multicast network, about their existence. Now this entire act happens completely in the gateway. And what it is happening to the source will send a multicast packet. It is an IP packet with a multicast destination. And as long as the FHR is a multicast enabled router, it is going to process that packet, it is going to realize that this packet happens to be a multicast packet, and it is going to get the source IP address of that packet, and create an S-conjugate state. This has both of those pieces of information completely enabled just by processing or capturing that packet. So source signaling, very easy. Receivers, on the other hand, will signal LHRs, or the last-hop routers. Now, just like FHRs are directly connected to sources, these routers, last-hop routers, are directly connected to multicast receivers. And just like sources, the receivers are signaled to the LHRs about their existence. Now, we've done some separate videos for both the source signaling and the receiver signaling, so I'm not going to go over a lot of details there. But ultimately, the receivers need a little bit more than just data layer. So there is a protocol called IGMP, or Improved Enrichment Protocol, that is used by the receivers. Or on the other hand, if you already know that perhaps the receivers, they for some reason do not form IGMP, you can always, on most implementations, statically program a receiver on an interface with the router configuration. So there are different ways to do it, but ultimately, FHRs should be aware of the sources, and the LHRs should be aware of the receivers. So now we're going to discuss actually what the network looks like once the initial signaling happens. So what is PIM-sparse mode challenge? Like any other multi-sparse protocol, it needs to connect FHRs, which are reportedly connected to the sources, to the LHRs, which are reportedly connected to the receivers. That is their definition, so we need to connect both of them. So here is the receiver network in the lower right-hand corner, and here's the source. Now, between these two is going to be actual multicast network. So this is just a network of multicast routers, they're all connected to each other. And routers are ones who are set on some sort of multicast routing protocol. They also run unicast routing. In this case, this is all PIM-sparse mode routers. Now, pay attention to the legend on the left side. So the origin chambers, that is actual multicast routing. These are routers that have multicast destination IPs and unicast source IPs. And like the blue color, it's the IGM signal that the receiver uses. So let's go into the source. The source is going to send a packet to a group. So now the G is really just that destination. The S is the IP of the source, meaning that the IP on that particular interface, right here, but we have the IP, ultimately that is the IP that R1 will see. Now, once R1 sees this traffic and actually processes this traffic, it can create that S-conjugate state. Once again, if you have the correct service, that would be multicast router protocols and multicast router protocol routers, and the receiving signal is sourcing. Right now, we're just going to skip those steps because they have been covered in another lecture. So R1 has S-conjugate state. Similarly, on the right-hand corner, the receiver is going to signal the IGMP to the last hopper. So R5 and R6 both have to be on the same subnet. They are both sending the same multicast streaming systems that will multicast on IGMP. And they both receive it, and they both process it. What does this receiver want to do? It just wants to join the group. So it doesn't really know the source yet. There is the So it's a star comma G join, whereas it wants a stream that comes out of that group G. But it doesn't really care about the source. If any source happens to send that stream, that should be delivered over to the receiver. So that happens as a signal. Once the multicast has been received from the source, the IGS signal has been received from the receivers. There are two states in this network. One R1, the VHR, you have an S comma G state, and on the VHR, R5 and R6, you have two star comma G states. And that's all that happens after the initial signal has been placed. The next piece here is really the central crux of PIM-SM. And this was the concept of the root. Let's recap that on that last slide. The FHRs now know about the source of the data was in the FHR. And the LHRs, we have two of them, know about the receiver. So they have these cascades from the source and the receiver. Now, if they could just somehow share this information, they could start connecting the source to the receiver, which is the integral of PIM-SM. One of the ways that they send this information, they send information to the directly, the FHR sends the FHR, the FHR reference from the FHR, the FHR choice from the FHR. Many different things are done there. Think of a scaling linear, many different levels. It's literally scaling linear to the level of PIM-SM. What happens if FHR is also an FHR? What happens if FHR doesn't really need that information anymore? What happens if FHR goes offline? How do you keep track of new FHR that's not here in the network? So it's really not the best idea there. There is a simpler solution. Think of a central registry. When there's a Bitcoin mine, this has to be that special registry. It is also called RB, and for the rest of the lecture, we may not be able to say what we're going to do because of these reasons. So RB from this point on. And what is the idea? It's extremely simple. Pick a single multicast router in your network. So the only limitation it has is that the router should be multicast. It should part of the network. It should be connected to other routers in the network and run multicast routing protocol. And you assign it some special duties. In fact, there are two special duties that it should assign. Number one, it should be able to receive multicast data information, from both the FHRs and the LHRs. So all the FHRs and LHRs should be able to send this multicast data information that they just gathered from the initial signal, and the RB should be able to accept and should be able to process this. Why does it process this? That's easy to do because if then you want to compare these pieces of information from the FHR and the LHR, and we're connecting those FHRs and LHRs if need be. And why would they need to be connected? Well, very simple. The FHR has information about a group G that the LHR needs to stream from. Star conjugate. So if those two pieces of information match, then the FHR needs to connect to the LHR, and the RB should proceed. Now the biggest, most important point here. The FHR, the LHR, and all of the other routers, including the RB, every single router in the domain must agree on who is the RB. Because if everyone has different ideas of the RB, now you have several different sets of registries, and then really how do you connect? There are advanced little concepts that we raise a little bit, but for the most part, for right now, for the production, this is not that all of them have to agree on what is the identity, what is the IP of this RB. Now, the RB just another multicast router. It has to be, that's the one thing I have to just go ahead and in your head. It's just another multicast router. Now, it forms these special duties, but the only stipulation is that it should be self-aware, that it should know that it is an RB. So in this case, let's choose an RB for our delivery here. Okay, there you go. So R2, we have just also decided that R2 is going to be RB. But the very first thing here to do is to form R2 of two new duties. So you select R2 and you should now go and put some declaration on R3, informing it that it is not the RB for the network. And it should really be a little bit responsible, right? So it's time to grow up. You're not an RB, you are an RB. And you have these special duties that you need to perform. Once the RB or R3 takes away that it is an RB, it is time to inform all of our other routers about this new identity of RB or new responsibilities that R3 has. So from R1 to R6, every single one of these routers now has to be aware that R3 is the RB. So if you need a multicast-sparse related duties to perform for you, you must make those requests to the RB. So if your RB is R1, R5, and R7, those are the most important pieces. They must know about the RB because they have to provide this S function, star function information for the RB somehow. We'll discuss that. But R2, R7, and R4 middle routers, they also need to be aware of the RB. So every router in this network is now aware, including the RB's self-awareness that it is also an RB. So the first point here is, let's connect the LHR to the RB. How do you do that? Well, for those who have already been to the PIM-SM lecture, there is that join group message. For those who haven't, just think of the message that the LHR is going to send to the RB. So the LHR has the star comma G state. And that's where it goes. So it receives some IGS signal from the directly connected receivers, and it can now start the PIM signal process. And what it's going to do is it's going to create a PIM multicast tree. The one thing to realize about PIM trees that they are built from the leaves, so from PIM outline branches and leaves, and they're built towards the root. As long as the leaf is aware of the root, they can literally tree to middle hoppers from the leaves to the root. The RB is considered to be the root for any star function tree. The star function tree, it's also called a one-point tree, that's specific, and it may be called a shared tree, that's more general multicast. But ultimately, it's an ASN, it's a source multicast tree. And RB, independently, is considered to be the root of this tree. So now what happened? Well, the LHR is the leaf of this tree. The RB is the root of this tree. So the LHR should really be able to signal the rest of the network to create a tree from itself to the RB. And for this particular reason, the LHR sends what's called a join increment message. Now, these are messages that are used for joins and increments in PIM. So this is exactly the same message that we dealt with in PIM-SM, but this happens to be join version. In PIM-SM, those are the pruners version. We prune ourselves from the tree. Well, right now, we're joining ourselves from the tree. One instance of this that we saw in dense mode was the graph access. We would graph users back to the tree. There was also an override that was literally just showing message. Updating your simulating the next router, the next router, so that UDRB, that you want to be part of this RPG tree. Now, this has sent something. So these most communication where they send out because it has a lot of interface on VDR. You calculate the RP interface with RP, or what we do unicast out of RP, and you send the message on that interface. So the RP address is found on RP's IP address. You identify that interface, one single interface, and you send this PIM join on. Now, this PIM join has a TTL of 1, so it's a hot by hot message. And it is directly with the RP versus that RP interface. Now, the next receiver router will do the exact same thing. It will process that particular message. It will create whatever states have to be created. And it further directed with the RP. So this message always is traveling with the RP ability to RP. And it is directed there by each middle hopper. So each router between the LHR and RP, it is further sending this message further and further to the RP. Now, as each router receives this join message and forces it to the RP, it will also create this RP state. Because that's the thing you have to create these RPGs free. And the free is really just a collection of all of the startup states on all the different routers. So the free is being built first, is being built from the leads to the root. And for that, the interface that receives the join. So we'll see this on the next slide, but on the middle router, so the router that's next hop to the last hop router, that interface that receives the join, the RP interface, that will be added to the array, or the outgoing interface. And the RP interface where the router is going to further relay this particular message, so it's going to send it with the RP. That RP interface to the RP becomes the incoming interface, or the IIF. So put those things combined and then create this tree. Let's look at how this actually going to happen. So the join messages that will have to be TRP, and each middle router should have that startup state. So let's get into R6. Let's talk about R5 for a second. There's a good reason for it, which we'll cover in the next lecture. But for now, just imagine that R5 has given all of its PIM duties for the particular segment, and it has transferred them over to R6. R6 is really the only other that we worry about. But R6 has the state courtesy of IG, it's like language. So now it can take that GB signal and create PIM signal out of it. So the PIM signal here is going to be PIM signal. And what happens next? Well, R6 is first going to find that RDF interface. So which is an interface that will easily take it with R3. Well, wouldn't it be this upstream interface? So wouldn't it be this upstream interface? So now, this is start RPG, this is an interface that's IIF. Because this is the interface, this is the interface where you should expect to receive traffic for this particular start RPG state. So this start RPG state now has interface available, courtesy of IGN, and it has an incoming interface. And if you remember from our protocol lecture, these are the pieces of information you need for every state for that to be complete. Well, let's go to the middle router, which is R4. But R4 is going to receive this join, it's going to process that join, and one of the first things that it does is it creates that start RPG state. So because it's processing, and it has an idea of who the party is, it has an idea that it is multicast router, or multicast router, does multicast protocol, it creates that start RPG state. But in addition to that, it is also going to remember the interface where it received the join. That is now added to the UI. And it's further going to try to find a way to relate this, right? So what is that interface? It's RP interface with RP. And if you look, it's directly connected to the RP. So identifying the RP interface is very easy. It's just a directly connected interface between R4 and RP, which is R3. So it's going to indicate that this interface now becomes IIF, or the interface, and it is further going to relay that join message up to the RP. And then RP says this is the first thing it does, is it creates that start RPG state. But furthermore, it is going to do something. It receives a join on interface. So that interface, once you create that start RPG state, that interface must be added to the UI. Now there is no interface on the RP, because guess what? RP is the root of this tree. So this tree really goes from R3 to R4 to R1. As I was actually troubleshooting out, it would be from R3 to R4 to R6, and finally that to the receiver. But that's the that is the start RPG rendezvous point tree. Now you know why it's called the rendezvous point tree. So if you look up here, it has several different names, and one of those is the RP tree. And that's really the name you should use if you're just configuring PIM-SM, because yeah, it's just a start RPG tree, that's probably also important. But it is really the rendezvous point tree. So right now we have one leg of the tree connected really LHR to the RP by purchase this joint groups, and R4 is aware that this tree, the shared tree, is now ready to carry some traffic. Now it's time for the FHR to actually connect also to the RP. But the FHR really cannot use that joint group message again, because where does the joint group message go? The joint group message goes from the leads to the root. And that's how, LHR actually joined the that's how they did it in PIM-SM. But this, if you look at it, think about it, this is not really a good solution for connecting FHR, or basically getting the information about sources to the RP. Because, yes, this joint group message was designed to build the tree from the leads, to build the tree from the leads towards the root. The message is sent upstream. Well, the source, where is the source? The source always is at the root. So that S-chronology tree, it is the LHR used to build that tree. So it is already at the downstream. There is nowhere further to send it out. So really, you do not be able to use the joint message for this particular source signal. So how does this signal actually happen? Think of this scenario. So what is FHR? It's simply took all the information that it had about the S-chronology tree, and it informed the RP about this. So all it tells the RP is that, so it informs the RP, and it tells them that there is this source that's connected to me. That is a network ID, there is an S-chronology state that I created. Don't you think once the RP has information about this S and this tree, it can then use its own joint group message? So this source as a node of tree, RP can then now leave that tree, and it can use this joint group message mechanism, and it can build a tree from itself to the source. So itself, the RB will leave the tree, and the source will remove the tree. Furthermore, the RB builds on an as-needed basis. So if it not goes through it, doesn't require that. So how do we price that tree? Let's start changing from there using the EHRs. So the RB will not have to build these sources that have rows that no rows are affected. So build trees to form the RB source, only for the rows that have affected. So if you remember, there is a special message called the register message. This is going to be used as type 1. Type of the message is 1. And it is one of the very few unique gas messages in PIM. We'll see how that actually helps us, how this message unique gas actually helps us. So if it's a gas message, it has no source ID. But that's very simple. If it's FHR ID, first off, router ID, what is the definition? Well, maybe you want to do the RB, so the definition is the RB is unique gas ID. So unique gas is there. And finally, what are contents? Well, there are a few things, but the most important content here is this SRG state. So you have to form the RB by the SRG so it can start to do the process if necessary. But ultimately, the most important information here is the SRG. For those people who have implemented this message before, or you come in a lot of detail in future lectures right now, SRG is what you should really concentrate on. So here we go. This is our state for so far. So we have the source that has built the EHR, we have received that has built the EHR. The EHR has also built the star RB tree or RB tree all the way to RB to the RB. So the next thing now, the FHR is going to send a unique gas, which is the message, to the RB. So here goes that message. And notice how that message, because it's a gas, it is literally just asking for RB has no interest in that message because there's a alert option in there already. So only the recipient may process that message. So that means any of the top routers, they will simply route or forward this message as it was in the packet. They will not look at the contents of that packet. So there's the reading. This message is not processed by the EHRs or in the top routers. So right now, if you look at that SRG state, because the message is unique gas, that SRG state appears in two places. So it is on the it is on R1 because it is really it's a top router. And it is correct that there is generated a series of multicast traffic. Once you send this PIM register message over to the RB is also going to create a state that's going to process that message as it has the technology information in it. And it is now going to create a PIM state. So the first state is really on R1 as a PIM state, but the state on RB is really a PIM state. So that, just look at the difference in the letter. This is the PIM state because it was created as a result of the PIM message. Now with this SRG state, you are going to take a look, RB is going to take a look at this S, and it is going to perform an RBF check on this S. So this S right here. The RB is going to take a look at it, it's going to create an RBF check on it, find out our RBF interface. That RBF interface, so the tree is really not built yet, but that RBF interface with this SRG state, really on tree, then becomes the IIF for this thing. For this SRG state, right now just have an IIF. You have no oil, so you just receive traffic on it, and see what you do with that traffic here. And really you're not building anything yet. There's nothing done here. There's SRG state on R1, because there's a traffic, there's SRG state on R3 and RB, which is because of the distance. And this is literally what R1 looks like right now. There's nothing else going on. Now let's look at what RB uses. What does it do? So we think that's the situation so far. RB has a star RB state, right? So it is at top of that 151 tree. And because this is the root of that tree, so it has a star RB state. Because this is the root of that tree, and there is no traffic yet on this tree, because we recently realized this discovery source, so there is no traffic yet. The RB also knows about an SRG state. And this is because of the system that's from the FHR. And there's the again, only the FHR and the RB has this information. Only the FHR and the RB, no other routers are aware of this particular SRG state. The RB now will relate the two pieces of information, so it will compare the SRG state and the RB state. And now it knows because of this G, so because of, in this case, G is not really just variable, it actually holds the same group, but because of the G being similar or the same identical group, or the same address, across both of those trees, SRG tree and SRG tree, the RB now knows that it must relay packets that receive on the SRG tree. So this has to receive the type C. But it must relay any packets that receives on the SRG tree, and it must relay them on the star RG tree, because they are individual receivers. And this is not yet, just give it a little more time to go through the lecture, and by the way, I think much better about it. Now RB will perform an analytic joint. So RB has an FSC, remember it has that star RG state, and it has information about this SRG state. But it really needs to join and show that free to actually receive packets. So remember, only the FHR and RB has this SRG state. So for the RB, it really must do an on-demand join, do that short span tree to first receive multicast packets. It must request multicast packets to come from the actual FHR. How do you do that? You actually make multicast tree for those systems to fall over. Now there are some optimizations that are built into this system, don't worry about it right now. For as much as it's concerned, there is no traffic yet. There's no traffic to build the tree. So it can use this join pruning mechanism because it knows about that root of the tree. It can use the join pruning mechanism to shortcut itself to the root of the tree. So FHR is considered to be the root of this SRG tree, source tree or shortest path tree. The RB will set that joint message, so once again this is the joint version of the joint message. And remember how we identified an IIF or incoming interface for the source on that last slide? This message is sent upstream on that IIF. So this simply is the RB interface on the RB for the source. Once again, this is processed by now the routers are actually going to process it, and it is directed towards the FHR from every router in the router. Now those routers that were, before this they really didn't have any idea of SRG state, now they can actually go ahead and create this SRG state. Because now they're actually physical access to this SRG state. Again, because we built the first, we built from the leaf to the root. And the interface that receives the join is literally seen as that start multi-tree. The interface that receives the join, that is in the interface list that now becomes part of the void. And then the RTS interface on each of the router, that is for the FHR or the source, should be the same thing. That is now considered the IIF for the start multi-tree state. Let's take a look at this in action. So once again, the RB needs to join this SRG tree to the start multi-tree, because it means that those packets flow from SRG onto the start multi-tree. And it says that join message to its source. So R3 is going to send a join message to the actual source with SRG. So now, if you realize, the other here changed. So the SRG page, do it. Here we go. It changes now that state to a signaling state. So it was basically the state created by the distance before it was zero. Now because we're actually doing, R3 is actually doing some point signaling for it, it becomes part of that PIM join. It's a pretty subtle difference, but it's a difference nonetheless, because now it will actually have an IIF, and it will actually have an actual state for it. So it's not just a self-created system. So first of all, for that SRG state, you actually do a RB check, so that RB check should be towards S or towards the FHR. And that then becomes your IIF. So once you have the IIF, the next thing to do is just send a message. So this particular message is an SRG. So this is not a SRG join, this is green number, but this is an SRG join. R2 is now going to process this SRG join because this is a hot bypass message. And R2 is going to do things. It's first going to create this SRG state because it has this for an environment dependent. And it is also going to take this interface where the message was received and add it to the void. This is added to the outgoing interface. Now it's actually going to do an RBF check, just like RB did. It's going to find an interface that takes this and towards the source, which should be this interface where it's the FHR right number. And this is now considered the IIF. So now you have a complete SRG state because those are the two things you need to state. You need the IIF, you need the void, and you have all three of those in R2. So R2 now sends this message further upstream to R1. And R1 already has that SRG state. So it doesn't have like, what's really simple, it's really big link, so I don't know whether you leave it origin or whether you leave it vertically. But, you know, we have other links and you go with that, but that state exists there already, and it goes straight to the link. And all R1 has to do is add this receiving interface into the void. So now you have a complete tree that goes from R3 to R1, if you're looking at this tree. So let's get a little green now. Or blue, yeah, we can use that. So for R3, because of all of these things, all of this signaling, the S-multi tree looks like this. So we already have this R-multi tree, and now we have this S-multi tree. So now it's actually going to bring those packets from the source to the receiver. So now the S-multi tree is built completely, right? So from the R2 to the FHR, it's actually built, and FHRs also have, you know, they're receiving those packets, and they also have the state. So what's the first thing that the FHR engine does? It now, because it has a void, so that's the important part, that's the part that S-multi signaling from what we actually accomplished. It has allowed the FHR to add a void in the S-multi state. So the S-multi state, before it was had that interface to the source. Now it has one. And finally, the FHR can start replicating the S-multi packets, and it is replicating on that void. Well, that void is connected to the MHR, right? So the MHR will receive these packets, the middle router. So they should be receiving their IIF if the tree was correct. They also put through the RBF check, once again, if the tree was correctly, the package should pass the RBF check. And then MHRs can further replicate them down the void. So receive the IIF, replicate it down the void, as we learned, so the packets eventually, hot by hot, go through all the MHRs that have those states, they will eventually reach the RB. Now the RB realizes that it built that S-multi tree, so if it's in order, these packets are going to have this S-multi tree. And the RB built that S-multi tree for a specific reason. It built it because it has a star multi state. So now the RB can replicate those packets to the S-multi on the star multi tree. And now that same process, if the packets are now traveling down the star multi tree, that same process is above. They packet the IIF, replicate them away, happen on the middle top routes that are sitting between the RB and the FHR. So really the star multi tree is also replicating packets now. Finally, we have confirmation the FHR receives these packets, and now we can really deliver them to recipients. So the packets are purposes and receipts have satisfied. So let's say we look at this in action. So the RB is now going to start replicating search traffic. So RB is going to send traffic from, the LHR, the FHR, first of R1 is going to replicate these packets, and it sends forward to R2 from R objects, and over to R3. Now R3 is the leaf of this S-multi tree. That's very important to realize that RB really, this is the end of the line for the S-multi tree. So for the S-multi tree, the RB has to be a leaf, so it has to process this traffic. And what it does, the RB, is that it processes this traffic on the S-multi tree. It now knows that traffic received from the S-multi must be related to the star multi. So that's what it does. It copies that traffic from the S-multi tree to the star multi tree. So the star multi tree then starts relaying this traffic on its way. Now this also relates to the hardware, and there's really no processing of traffic in general, since there are things that are built according to the specification. But this is the mechanism of the protocol. So once again, receives the traffic from R2, processes it on the S-multi. Sends it, because it's on the S-multi, it now sends down star multi. This is the tree being connected. This is the shared tree being connected to the source tree. And now because those packets have been sent on the shared tree, send them down the way. If you send them down the way, R4 is going to receive the IIF, send it down its way to R6. R6 is going to receive the IIF and send it down to the receiver. So now you can see we're actually multiplication of the multicast traffic is flowing from the source to the receiver. And this is the basic crux of PIM-SM. Connecting things, the those S-multi trees, the linking star multi trees, the FHR forming the RB out its existence or the existence of the S-multi, and the RB finally working to connect the S-multi to the star multi. This is basically the 10,000 foot. It's a very high level. It's very important to simulate this ahead before we move on to the next lecture. Because the next lecture is actually going to deal with the details of the PIM joint message, or the star multi joint message, or the S-multi joint message. or what the actual digital message looks like. But really, if you go over this lecture as well, just ahead, you can finally create this by yourself. I would say that we're going to move on to the next lecture. As for this lecture, I really hope you enjoyed it, and I hope you can move on to the next lecture. Till then, thank you.
Okay, so he says he wants us to be able to create that screen by ourselves. The drawing he had there, I can't do that right now. Yeah, this was a great lecture. I'm really really glad for this, but you know, it's this problem here. If this topic has this much depth, but this much points, is it worth getting like so caught up in it? So I think between videos like tonight and stuff, I think outside of this series I'll be watching the rest of these. I'll be prioritizing these videos more just because of how good they are. And I'll want to watch these as well. But they're really long, and there's a lot of them. So, shoot, I've got a lot ahead of me, and I'm very rapidly ticking off time. But this is how I chose to spend this video. I don't think it was necessarily a horrible choice. I would have liked to have gotten more hands-on, since the test is only hands-on. But if I don't understand it conceptually, I'm not gonna like understanding the concepts, as I've said, are the most important thing, and then I can use help apropos. I can question mark out to just figure out how they implemented it on the actual device. But if I don't understand what I actually need to do and what the concepts are, then I'm completely lost. So that's going to be it for this video. Stay tuned for part 2.